In the classical days of science, scientists wonder why hot metals emit different colors of light. As time goes on, scientists such as Max Planck discovered that electromagnetic radiation emitted by a black body depends on the frequency of the radiation and the temperature of the body. In our flame lab, we execute this theory by dipping wooden splints in metal salt solutions and heating them up using a Bunsen burner to see the different colors that each metal salt solution produces. The purpose of this experiment is to gain a deeper understanding of how electrons work and how to identify the elements by their color. If the metal salt solutions are placed upon a Bunsen burner and produces a color, then that color should correspond to the color that the elements are known for. The materials used in this experiment is a Bunsen burner, 9 wooden splints, metal salt solutions, and cobalt blue glass. Procedure. First, we make sure everything is set up. There should be 9 distinctive metal solutions. There should be 1 wooden splint placed in each metal salt solution. It's necessary to light up the Bunsen burner and have it ready to go. Secondly, a dipped wooden splint is placed inside the blue Bunsen burner flame. The color of the blue fire is changed and the color that we observed is recorded. When recording the color, it's important to see the initial color given off, not the yellow-orange color produced afterwards. Then, this process is repeated for every metal salt solution. Finally, the blue cobalt glass is used for the sodium-potassium mixture because it gives off a different color when the blue cobalt glass is used. Now, let's check out what I observed. I saw lithium with hot pink, barium with yellow, scrotium with red, calcium with orange, sodium with orange, copper with green, potassium with light purple, sodium potassium with orange, and sodium potassium with cobalt glass with pink, and unknown with deep red. And here are the calculations for copper, calcium, and strontium. Here is the results. Notice how energy in joules and frequency of the element decreases while the wavelength increases. This is the basic rule for all Roy G. Biff spectrums. Remember that an electron moves first from a ground state, then low energy, to a high energy in the atomic emission spectrum. This is when the element is absorbing the Bunsen burner's flames. When the electrons in the elements get so excited, they can't hold it anymore, so they release their energy in the form of flame colors. How much energy the elements releases depends on how much they can absorb. This is why elements can be identified with distinctive colors. In conclusion, we found out that flame color changes happen because of the atomic emission spectrum. It is safe to say that the colors from the flame of the elements correspond to the identification of the elements because flame color matches the energy calculated from our results. One problem with our lab is that we placed the wooden splint too low. Placing the wooden splint on top of the Bunsen burner's blue flame would give us more accurate results. Sometimes the wooden splints didn't dip enough into the solution, which resulted in little color showing. We also had difficulties looking at some flame colors with the light on. It was difficult to see if the color was orange or yellow. The atomic emission spectrum can be compared to the northern lights. Just like the elements in the flame test lab, extremely hot gas particles from the sun's atmosphere go into the Earth's atmosphere and collide with Earth's hydrogen and nitrogen atoms. The hydrogen and nitrogen get so excited that they produce colors in the Earth's atmosphere, resulting in a beautiful sky.